could remember it, but it's been a while since everything was okay.
Okay. All right, on YouTube, you should be able to hear me now. So I think what that means, so somebody just let me know that the mic was muted. Yeah. So apologies, I did not know until 11:23, but it will be, yeah. As of now, it's not muted. However, you should still have access to the Zoom lecture. So I will make sure that you have a link to the Zoom lecture, and I'll provide a link on the home page so you can get to that as well. Okay. All right. Thank you for letting me know. I do appreciate that. I think mostly everybody's tuning in via Zoom. So, all right. So H4. P4, what was that? 250 PSI? Ooh, this is state 4S. So 250 psi and an S4S, which is equal to S3. Okay. All right, so let's see what it is. 693.53. Okay, and then for state 4, isentropic efficiency, H4S minus H4, oops, I'm sorry, H4S minus H3 over H4 minus H3. And that's where we're going to get our H4 value. So our H4 ends up being 705.92. Perfect. Okay. All right, so let's see. State 5. I think the rest of them are going to be pretty straightforward because we got some throttling processes coming up. It really shouldn't be too bad. Let's see. Make sure you can see that. There. Anything to be off screen. All right, so state 5, I've got a quality. So my quality at state 5 is 0. And my pressure P5 is 250 psi. So let's see what I've got. 167.77.
Yeah, that's what I got as well.
Perfect. Perfect, perfect. And then state 6, going through an isenthalpic throttling process through the expansion valve. So H6 and H5 are equal to one another. And then state 7 and 8 are very similar, right? 7 to 8 is a throttling process. Let's actually look at our diagram there. So 7 and 8 should be the same enthalpy, and it does say in the problem statement that saturated liquid enters each expansion valve, so the quality at 7 is 0. So isenthalpic H7 and H8 are equal to one another, and then H7, oops, yep, our quality is 0, and then the pressure, of course, is 80 psi. So it's going to be the H sub F value at 80 psi. I've got 91.22. Okay. Perfect. All right, so I've got all my H values. That's the most annoying part. And so now I can go through and kind of figure out the other stuff that I don't know. So I wanted to find the power input for that first compressor. And so I've got the H2 and I've got the H1 values, but I don't actually know MDOT. However, if I look at I'm going to kind of scroll up, but I'll come back. If I look at the diagram here, the information that I'm given that gives me anything about the rate at which things are going on would be my Q dot N. So I know, let's put that here. So I'll say where my M dot 1 would just be Q dot N divided by, would be H1 minus H8. All right. So let's make sure we got the units correct on here. So we've got H1, got 604.61. It's H8, 91.22. And this is BTU per pound mass. Okay. And then up at the top, we've got 30 tons Right, yeah. And I know that, what is it, 200 BTU per minute is 1 ton. Perfect. So I get a mass flow rate of 11.69 pound mass per minute. So 11.69 pound mass per minute. And so when I plug things in here into my W.C1 equation, ooh, actually let's do that down here because I do have some unit conversions that I have to worry about. So this will be, I'll do it like that. There we go, fixed it. So my W.C1 is equal to 11.69 pound mass per minute. And then H2 minus H1 move you over here. So my H2 is 707.59. And H1 604.61. And that's BTU per pound mass. And then I think I do have some, I got some unit conversions to put it in terms of horsepower. So kind of this a little smaller here. So 1 horsepower is 2545 BTU per hour. And an hour is 60 minutes. And I think that should make all my units work out correctly. So my W.C1 ends up being 28.38 horsepower. Okay. Okie dokie. Let's get the other stuff. So yeah, there's that guy. And then I do need to get the W.C2. So let's do a little housekeeping here. Kind of separate some stuff. Okay. Oh, and I never got a number for that M.3 over M.1, but I do have it. It's 1.353. Okay. And then my W.C2, I don't know why I'm putting them over here. Let's put them all the way to the left. So W.C2. So this is going to be what, between 3 and 4? So W.3 or M.3, I'm sorry, times H4 minus H3. Where that we already figured out M.1, and I've got the relationship between M.3 and M.1. So, I could just say, well, this is 1.353 times M.1, right? So I'm getting that from this guy up here. And then it'll be H4 minus H3. So I showed the unit conversions already right above it to show us how we're going to get in terms of horsepower. So I won't do it again. I'll just kind of put a note there that that's what you do need to do. But 30.81 horsepower. Alrighty. And then the very last thing I was supposed to do was the COP, I think. Yeah. So your COP for a refrigeration cycle. So it's what you're interested in, and for a refrigeration cycle, it's going to be Q dot in, or Q dot coming from the low temperature reservoir over the net W dot net in, which of course in this case is our, what, might as well just put this in, well, yeah. So it's going to be, let's put it in terms of M dots and H's because, you know, that would be useful. So my Q dot N would be going to be M dot 1 times H1 minus H8. And then your W dot net in, I've got an equation for that as well. So what is this going to be? W dot C1 would be M dot 1 H2 minus H1 plus, then I've got W dot C2, which is this guy right here, right? It's, in fact, I'll leave it as, I'll put it as M dot 3 times H4 minus H3, where we know what M dot 3 is. I'm going to kind of zoom in here. I'm going to rewrite most of this. H2 minus H1 plus it's fine. M dot 1 H1 minus H8. And I know what M dot 3 is. It's up here. I know it seems strange to be writing it in all of these terms, but I want to at least show you how we can get it. You know, sometimes it might be good to have things in variable form, and that way if you had a problem on your test where you were supposed to write things in terms of variables and show you how you would simplify to get the governing equation, you know how to do it. Oops, sorry. So that M dot 3 would just be M dot 1 times H7 minus H2 and I'm going to zoom in on this in a second, over H6 minus H3. That's your definition of M dot 3. And then of course, get a H4 minus H3. And I do finally get an answer. I know we could just, I mean, we have numbers and everything, and that's fine. You could plug it in and calculate it, but I think it's a worthwhile exercise at least. So 2.39, that's our COP. Okay. So let's see. I think we had one more problem, and that was at the very end, if I'm not mistaken. And it's probably going to seem like, why are we waiting until this point to solve it? Because it's really simple. Right? You would think that there would be a really complicated problem being the last problem that we get to, but no, it's not. The only difference is it is a heat pump. So, and I think most of the cycles that we've done, they're refrigeration cycles. We call them a refrigeration cycle, and we are calculating the only thing that's different is we refer to refrigeration capacity, which is the rate at which heat is coming into the cycle from that refrigerated space. And then we define our COP based on that refrigeration capacity. Problem 10 refers to a heat pump. So, yeah, let's write this. So vapor compression, and it's simple. meaning that there are only 4 processes. So from 1 to 2, you have an ideally isentropic compression process. And someone mentioned in class the last time that they noticed that we drew the compressors. Sometimes we draw them, you know, like maybe you draw it like, actually, there were 2 different questions. Sometimes we draw it like this. So a compressor going like this. I'm going to erase this in a hot second, but just want to, sometimes we'll draw it like this. Oops. Stupid, stupid, stupid. I just drew it the same way. Okay, there we go. Sometimes we draw it like this. Okay, so, right, maybe it's flipped a little bit, but the way that I'm indicating whether or not that it's, or the way I'm indicating that it is a compressor is it's going in at the fat end and it's coming out at the skinny end, right? So, yeah, being compressed all the way to the skinny end. And somebody else commented that we've drawn it like this in class, and there are some problems in the book where they have it that it looks like this. And it doesn't really matter, number one, how you draw it. We're analyzing it the same way. Right, this guy right here would be a reciprocating type piston cylinder compressor. These guys would be centrifugal or axial designs. It does not really matter. Does not matter. There we go. Doesn't matter for our purposes. So I think I'm going to draw it like this today, but it doesn't matter because we know that it's just a compression process. So 1 to 2 is an ideally isentropic compression process. And then we have a constant pressure heat rejection process to a high temperature reservoir. So that is our, yes, it's live. Yeah, it's live on YouTube. It's also live on Zoom, and the link is on the Canvas page. It will be available on Zoom. It will also be available on, it will be available after class on YouTube, but it will also be available on Zoom. And just be aware, if you're watching the YouTube one, the first few minutes, the mic is muted, but it will not be that way on Zoom. So you can access the video in both formats, either Zoom, which you'll be able to access through Canvas, or YouTube, which you'll be able to access on the YouTube playlist. So this is Q.out or Q.h. And then you've got your expansion process down to lower pressure. So this is 3, this is 4. And then you've got a constant pressure heat addition process from your low temperature reservoir. So this would be a Q.N, or you could call this Q.L because it's referring to the low temperature reservoir. All right, so let's go look at our problem statement. So we've got R134A. It provides 35 kilowatts of heat to a dwelling. So that's this up here, that's our dwelling. And 35 kilowatts, that's a rate term. So it's Q dot. On a day when the temperature outside is below freezing, saturated vapor enters the compressor at P1 1.6 bar. And then saturated liquid exits the condenser. So on your test, you may see things drawn like as heat exchanger, but maybe it doesn't say whether it's a condenser or a condenser or evaporator. But right, know what's going on in that cycle and the point of it. So goes in, your working fluid goes into that compressor, it's compressed into the superheated region, right? It's got a very high temperature, it's got a lot of energy associated with it. And the next heat exchanger it's going through, the purpose of that is to extract that energy. And as it extracts that energy, your working fluid is going to decrease in temperature and it's going to condense. So this is your condenser. So saturated vapor exits the condenser, which operates at 8 bar. Oops, P3. Okay, determined for isentropic compression.
Professor?
Yeah.
I'm curious, what's dwelling in this case here?
Where you dwell, your house.
For the cold temperature.
So like the heat pump at your house, the way that it works in the winter is it's pulling heat out of the air outside. So even though it's cold air outside and it doesn't feel like there's any heat, there's still thermal energy. There's still heat, thermal energy in the air outside. So this is just the cold outdoors. And the way that that's happening is because your refrigerant that's circulating in that loop, when it passes through your evaporator, when it passes through that evaporator coils, at that point, right, it's already cooled down in the condenser. It's also, and then it's cooled down even more as it's gone through the throttling process. Pressure goes down, temperature goes down. So now it's really cold. And so to the cold air outdoors, you know, the outdoors is now at a higher temperature than the refrigerant. So heat's going to flow from what's hotter, the cold outdoors, into what's colder, the refrigerant.
Gotcha.
Yeah. Okay. You're welcome. So we want to find the mass flow rate in kilograms per second. Then we want to find the compressor power. So that's this guy right here, W.C or W.N. And we want him in kilowatts, and then we want the coefficient of performance. And this is a heat pump. He's operating as a heat pump. So we're looking for the coefficient of performance for a heat pump. I'll throw my assumptions right here. So same assumptions I typically make: steady state, changes in kinetic, changes in potential energy are negligible, and it's an ideal cycle in that there's no heat transfer where I don't want there to happen, where I don't want it to happen or occur, which would be the case for the compressor, right? You want that to operate adiabatically. It also tells you there's no fluid friction causing a pressure drop in the condenser or the evaporator. That's I'm so sorry. P2 is equal to P3. P4 is equal to P1. Okay, so here we go. So first things first, probably our M dot. So only thing that tells me anything about what's going on is the Q dot out. And this, by the way, just like we could define a refrigeration capacity for a refrigeration cycle, this is the heating, this is the heating capacity. It's the rate at which you're heating that heated space. So refrigeration capacity would be something defined for a cycle that's operating as a refrigerator, and it would be the rate at which heat is being removed from the refrigerated space from the low temperature reservoir. And for a heat pump, we would define a heating capacity, which is the rate at which you're heating the thing that you're interested in heating your house. Okay, so it's going to be Q dot out. It'll be H2 minus H3. And we'll get those H values in just a second, and then we'll call it. W dot C, well, presumably at this point we will have found the M dot, and there will be no problem in defining this as M dot times H2 minus H1. And then your COP, your COP for a heat pump, it's what you're interested in. What we're interested in here is heating our heated space, Q dot H or Q dot out. And then we're interested in the, should have color coded this. We're interested in the W dot net in, which would just be the W dot N. Okay. And so I've got M dot times H2 minus H3 on the top. M dot times H2 minus H1 on the bottom. And those guys cancel out. So this is R134A. I'm going to just go ahead and I'm going to give you these values with the assumption that you could probably look them up. I don't want to waste anybody's time. But let's kind of go through and think about the intensive properties that we know at each state. So for state 1, yeah, you've got the quality and you've got the pressure. At state 2, your two properties that you know the pressure because it's the same as state 3. And then you also know S2 because it's the same as S1. So there's your two independent intensive properties. Here's your two independent intensive properties for state 3. And then state 4, it doesn't really matter because it's a nice enthalpic throttling process, so you're good there. So I've got for state 1, 237.79. Or I'm sorry, 0.97, apologies, I'm so sorry. 0.97 kilojoules per kilogram. H2 is 271.22. And H3 is 93.42. All right, perfect. So I'll go ahead and give you these answers, and then I'll answer any questions that you have like right away. And other than that, I will hop on over and just hang out in office hours until 12:30. This guy is 6.55 kilowatts, and this guy is 5.34. Okay. So if you have any questions, you could chat it, you can throw it in the chat, or you can, when do you think the homework will be graded? I think that's probably what you meant. So yeah, I'm aware there's like a short compression time, and I want you to be able to have all the information available. So the homework answers will be provided to you at 11:59 on Saturday night. So I've got an announcement set to go out right at that time, so you're not waiting on anybody to grade your work, and it'll be a fully worked out solution.
Hey, Professor.
Yeah,
Can you scroll back up to number 9 real quick?
sure. Oh, problem 9?
Sorry, no, the one we just did.
The one we did today, okay. Yeah. Actually, how's that? That's probably a little bit better. You can actually see that.
Okay, sorry, I just missed one of the answers.
Sure. Yep.
Wait, Professor, did you say you're having office hours with us right after this?
Yes. So depending on how you've got your notification settings kind of set up within Canvas, you may not have received. Depending on your notification like settings and frequencies, you may have not received it, but I did put an announcement on Canvas that I was moving office hours just today to right after this class, and it'll be virtually, and the link is in there. It's just in my personal room, and you just hop on. You know, I'll be there. I'll just be hanging out.
Like on Zoom? No,
Mm-hmm.
like I'm on Canvas page right now. I don't see it.
Go to announcements. Go to announcements.
Okay. Okay.
You see it?
Oh, okay. I see it now. I'll go there. I'll
Okay.
Thank you.
All right. Yep. All right, guys. So I'm gonna hop on over there. If you do have questions, that is where I will be. Okay. All right. Have a great day, guys.